Welcome back. This is lesson 4 of Machine Learning Zoomcamp session 8. And in this lesson, we'll talk about convolutional neural networks. Convolutional neural networks are the type of neural networks that are used for images mostly, and they consist of different types of layers. One of them is called convolutional layer. That's why they have this name. And I will give you some intuition how they work. And actually, the model we used, this exception model, is a convolutional neural network. So let's see how they work. So we have an image and we want to use a neural network, a convolutional neural network, to predict what kind of image it is, what kind of whole thing is there. So let's say we have a neural network. So this is our, so I'll call it CNN, which is short for convolutional neural network. For now, let's say it's a black box. It gets an image and then outputs prediction. What happens inside is that there are different kinds of layers, layer 1, layer 2, and so on. There could be quite a few of them. Let's see, this one is 2, this one is N. Two main types of layers for convolutional neural networks are, so first are convolutional layers, and then second is dense layers. So let's first talk about convolutional layers. Convolutional layers consist of filters, which are kind of small images. They're usually quite small images, like 5 by 5, could be even smaller. And there are quite a few of them. Let's say 6 for this example. These images, filters contain simple shapes like this, basically simple lines, simple shapes. This is just an example. This is not from a real network. It's just to give you some understanding what might be happening inside the neural network. So we have these filters, and then we take our image, this t-shirt, enlarge it a little bit. So we take our image, we take a filter, and we slide this filter across the image. And every time we apply the filter to an image, we see how similar this filter is to the part of image. So let's say we have this table. So we have this table, and when we slide our filter across the image, each cell here in this table corresponds to a particular position of the filter on the image. And then we take the filter and take the part of the image where this filter is on right now, and we calculate the similarity between them. This is just a number. 0 usually means no similarity, and then some higher number, let's say 9, 10, or whatever, it means bigger similarity. So we take this image, and then for each position we see, okay, here it's 0 again, it's not really similar, and so on, right? So we slide it the first row, right? And we do the second row. It's again not super similar, and so on. Maybe we see this part, right? So this is like a circle. So when this image is here, then with this filter is here, perhaps the corresponding part of this table will be somewhat similar, right? And then the rest, like when we move, is not really similar. So maybe the rest will be zeros as well. This array is called a feature map. And this feature map is a result of applying a filter to an image. So we slide a filter across the image, and every time we calculate the similarity between this particular filter and the part of the image, we record the result, we get this feature map, and higher values mean higher degree of similarity. Similarity between the filter and the part of the image. For this filter, this part here corresponds to this cell, and this part here is not really similar, so then that's why it's 0. Right? And we do this for each filter. Here we have 6 filters, and for each filter we have a feature map. Let's take our image. Let's take some of the filters. So we take our image, we take the filters, and then as the result, we have multiple feature maps. So it's actually one feature map per filter. So the input is image, right? And the output are feature maps, as many as there are filters. So let me just go to the next slide, remove filters. So the output of the first convolutional layer is a set of feature maps, convolutional layer 1. But then we can take this output and we can treat it as image, a new image, an image that we made from the original one. And then we can have another convolutional layer. This convolutional layer has its own set of filters. It applies these filters to the image, not the original image, but the one that the first convolutional layer produced, and then it produces its own feature map. So maybe in the first case, we had 6 feature maps because there are 6 filters, but maybe the second one has 12 filters. So it produces 12 feature maps. We can keep going. Then there could be a third convolutional layer with its own set of filters that produces a bunch of other feature maps. And because of this chaining, each layer learns more and more complex filters. These filters, actually, this is something that a neural network learns during training. So each convolutional layer can get more and more complex filters. So for example, the first layer, this is convolutional layer. We can have 3 of them, let's say. It's convolutional layer 1, 2, and 3. The first layer learns simple filters. So these filters could be simple shapes, like just stripes. But for the second and the third layer, the filters it learns, they can become more and more complex. So for example, this one can have some angles, maybe circles, crosses, and so on. And the way the second layer learns these filters is by combining the filters from the previous layer. So for example, circle can be a combination of these two. So we put them together and we get a circle. So the angle could be a combination of these two, right? And basically every angle could be a combination of these two, and you put them differently, and the cross could be a combination of this and this. So you have these simple shapes, then you combine them and you get more complex shapes. Then by the third layer, you have even more complex shapes, maybe something like this. The first convolutional layer can recognize simple patterns. So it can recognize this kind of stripes, like this kind of stripes. So for this part here, this will get activated, get high similarity. This array here will have high similarity with this shape. And then once we pass the image through the first convolutional layer, we get a feature map. And using this information, we can detect more complex shapes. So here, for example, we can detect a circle, or here we can detect these angles and so on. And in the third layer, we can maybe already detect sleeves and so this thing perhaps, and so on. So each layer can detect progressively more and more complex features. This is like low level. So this would be mid-level. And these are more high-level features of the image. And by features, I mean like, okay, there are sleeves or there is a circle in a specific area of the image. These are the sort of features of an image. This is actually not exactly how filters look like, but we can think of them in this way, because actually what filters do, if they you can see here, let's say we have a filter here that we apply to some area here, and then it looks at this region across all the values of all the feature maps in this particular region. So it kind of goes in depth here. It looks at all the different feature maps So for example, one feature map can be this, and then the other feature map maybe this one. And if we see that they are together, the first feature map has high similarity, I don't know, number 6 here, and then the second one also has number 6 somewhere close, then we see, okay, they both have high value here. It means that it can form a cross. And in the same way, the higher level filters from the third layer, they're using the feature map from the layer 2. This way, the more layers we have, the more complex features we can capture from the image. And remember that all these things, actually, they are learned. So you don't need to sit there and tell a neural network, hey, make this kind of line. It just learns them automatically. So we take our image and we pass it through a set of convolutional layers. And the result of this is a vector representation of image. So let's say if our input image is 299 by 299 by 3, then the vector representation could be something like 284 and just this. So this is a one-dimensional array, and this way we turn an image into vector. And this vector captures all this information about the image. So all these features, all these filters that we saw, they extract features from the image, and there could be some regions of this vector saying that there are sleeves, for example. There could be an area that corresponds to a color. There could be an area that corresponds to, I don't know, this part of the image and so on. There are some numbers. It's very hard to make sense of these numbers for people, but for neural networks, they make sense and they contain all the information that the neural network was able to extract from an image. And it's a vector, so it's more convenient now to use because it has all this information. Now with this vector, what we can do is we can build some dense layers, and we will talk about these layers now. And these layers will turn this vector representation into actually final predictions. The final prediction is too short. So the role of convolutional layers to extract this vector representation. The role of dense layers use the vector representation to make the final prediction. So now let's talk more about this vector representation. So this vector representation consists of many numbers. So it could be the dimensionality of this vector could be 2048 or 1024, something like this. Usually it's powers of 2 for some reasons. And remember that was actually extracted from our original image. So it's our original image turned into a vector, and it contains a bunch of elements. Now, using this vector, we want to build a model that makes a prediction. Let's say we want to make a binary model, binary classification model. Is this a t-shirt or not? So this is our x, and our y could be 0 or 1. 0 means not a t-shirt, and 1 means t-shirt. And what do we do in this case? Usually we use something like logistic regression. So then our function g from x, which is this x, which is the vector representation of an image, our g looks like sigmoid, because this is binary classification, this logistic regression. So we have sigmoid, we have our features, and we have our weights. These are the features, and the weights are trained. So we need to train a logistic regression model to get these weights, to learn these weights. And then the output of this would be probability that this x is a t-shirt. So let's build a model like that. And now I will use a slightly different notation. So now I will put all the elements of our array X, our feature representation, as circles. So we have X1, X2, X3, and so on. And then we need to make a prediction. So for that, we take all these X's, we multiply them by W's. So for x1, we have W1, x2, we have W2, x3, W3, and xn, Wn. So we actually multiply them. So an arrow here means take x, multiply it by W, and then sum them. Right, so we sum them all together, and then at the end, what we do is we take this sum and then turn it into probability by using sigmoid. So this part here is sum of all the x's and w's, and this part here is sigmoid. Then the output of this is probability of being a t-shirt. This is how we do this for binary classification. Let's imagine we want to build a model for multiple classes. So let me copy that. So in addition to t-shirt, let's say we will have a shirt and we will have dress. For that, we can build 3 models, one for shirts, another for t-shirts, and then the third one for dresses. And then, so we'll have now a model for shirts that also gets the same input, and then it sums it. And then for this model for shirts, there are also W's. So W1, W2, W3, W4. These are different W's. So they are W's for shirts. And then we can also have the same thing for dresses. And here it would have different set of W's. So I should have used different colors here. So let me change that. So for t-shirts, we will have red W's. For shirts, we will have green ones. And then for dresses, we'll have blue one. So now we have 3 models, but instead of using sigmoid in this case, we actually should have something different. Maybe remove sigmoid. I'll put think like that here. So sigmoid for multiple classes is called softmax. Similar to sigmoid, but it's a generalization of sigmoid to multiple classes. And then the output will have 3 numbers. It's 3-dimensional output. The first component will contain the probability of this X being a shirt. Then the second will be probability of this X being a t-shirt. And then the last one, probability of this X being a dress. We have quite a few errors here. We can make it simpler. So we have our input, and then we have the output. The output contains 3 components. So the first one is shirt, then t-shirt, and dress. And then here we have softmax. And we can just use one arrow here to say that there is a connection between this X, our vector representation, and the output. So this is input. And if the vector representation contains t-shirt, then prediction would be t-shirt. So this will be our prediction. So what we see here is we put multiple logistic regressions together, and as a result, we got a neural network. I'll put it on another slide again. Let's remove that. Actually, the softmax part for us is not currently interesting. So let me remove that. So let's say we have a network, neural network like that. So this layer is called dense layer. This is the input to the dense layer. And this is the output of the dense layer. The reason it's called dense is you remember that each element of the input is connected to each element of the output. So we have something like that here. It's a lot of connections. This area here is pretty dense. So it's dense because it connects each element of the input with each element of the output. And the actual transformation here is called a dense layer. And remember that for each of these outputs, we have a W, so we can call for this one, so let's say W1, for this one, it's W2, W3. And if we put all these W's together, we get one big W. And this W, it has all the W's as rows. And then if our X is a column vector, then to actually transform the input to output, all we need to do is multiply W by X. So a dense layer is nothing else but matrix multiplication. And we can put multiple dense layers together. So let's say we have one dense, we have our input, our vector representation, then we have one dense layer, and let's say we have another dense layer. So this is our vector representation, and this is our output, and the layer between is called inner layer. And it's more like, actually, this one is more like output of the inner layer. The actual layer is here, the connection between outputs. So this is first dense layer, or I would say inner dense layer. And this would be the final dense layer for predictions. Let me move it a little bit. If we go back to our problem, actually predicting the type of clothes. So we get our image here, we turn this image into a vector, then it goes through, so there is some vector representation. Then we convert this vector representation into some inner representation, and then we finally convert it to output. And then from this output, should be 10 of them. We select one with the highest value, which hopefully should be t-shirt. Yeah, so let me summarize it a little bit. So we have a t-shirt, then we use convolutional layers to turn this t-shirt into vector representation, vector form, and then we have a bunch of dense vectors to get the final prediction. So this is convolutional layers, then it's our vector representation. Then we have a bunch of dense layers and prediction. So here, of course, I only scratched the surface of how convolutional neural networks work, how they might look like, what they do inside. Actually, I recommend to check this website, the course I mentioned, this CS 231N, Convolutional Neural Networks for Visual Recognition. So they go into a lot of details how these different layers work. So we talked here about convolutional layers. And let me find them. So here they talk. So this is what's actually happening to an image. Yeah, so this is feature maps that we talked about. The convolutional layer. Yeah. Then so these are the filters that a neural network learned. So you see that there are different stripes and color or a bunch of colors. Yeah, so these are the kind of filters that a neural network learns. There is a very nice visualization. Yeah, so this is how convolutional layers look like. So if you want, you can check and see. It's a very nice visualization. So so these are the input, the image actually. These are the filters, and then the filters are applied. So they are applied like there is a sliding window, slides through the image. Right? And then each time it slides, they compute this volume. So this is the what we call feature map. There is one type of layer that we didn't talk about. It's called pooling layers. And the purpose for pooling layers, maybe I'll just quickly mention, is we have this feature map. So let's say we have this feature map that one of our convolutional layers learned. And what pooling does, it takes it and makes it smaller. And the reason it's doing it, it's for making a neural network smaller, for forcing it to have fewer parameters. Let's say if this one is 200 by 200, after pooling it will be 100 by 100, for example. So it will shrink it 2 times. So yeah, if you're interested in this, you can go through some of the course notes here. They're really good. It's not required that you go through them, but if you're really interested, I suggest you check them. And I think that's all for this lesson. So it was a bunch of theory, and actually in the next lesson, we will see how this theory was useful. So in the next lesson, we will see how to use this part for extracting vector representation and how to train this dense layer for our purpose. So see you soon.